Well, thanks very much, Emily. And good evening, everybody, and welcome to this evening's Heinz Pagel's Memorial Public Lecture. As Emily said, I'm Paul Goldbart, Professor of Physics at Stony Brook University, a former general member and now honorary member of the Aspen Center for Physics. The center's members are people from the international physics, astronomy, and mathematics communities, who, along with others, volunteer time and expertise to operate and guide all aspects of the center's activities in partnership with the center's small, terrific staff. The late Heinz Pagels, whom this lecture series memorializes, was a physics professor at Rockefeller University, president of the New York Academy of Sciences, trustee of the Aspen Institute, servant of this center for 20 years, and a part-time Aspen resident. He was also president of the International League for Human Rights. Because he devoted a substantial part of his life to the effective public dissemination of scientific knowledge, his family and friends instituted this lecture series in his honor. Having myself returned to Aspen annually for some 20 years, perhaps I might say a word about the center and its extraordinary role in science. This is a truly fabulous institution, widely and rightly valued as a global treasure. Why? Because it enables researchers from around the world, many at the forefronts of their fields, to congregate, to interact with one another, inspired by one another and the beautiful surroundings, and to freely exchange ideas about cutting-edge research through presentations and, importantly, through extended, informal conversations. In short, because of the center, among the most creative minds in science can come together every summer to dream about some of nature's most fascinating and significant puzzles. Informal atmosphere and loose structure are what make the center unique and are keys to its stimulating vibrancy and extraordinary impact. Today's speaker is a splendid example of the excellence the center attracts. Vedika Khemani is a professor in the Department of Physics at Stanford University, where she's also affiliated with the Department of Applied Physics, Institute for Theoretical Physics, and QFARM, Stanford's initiative in quantum fundamentals, architectures, and machines. Following undergraduate studies at Harvey Mudd, doctoral work at Princeton, Vedika spent 3 years at Harvard University as a member of the Society of Fellows before joining Stanford in 2019. Already, Vedika's research has shown an admirable blend of depth and impact, focusing on some of the most essential questions in contemporary quantum physics and connecting to potential applications in quantum information processing. I mention in particular her widely cited works on many-body localization, organization in driven quantum systems, and her theme for today, time crystals, all valued not only for their technical power, but also for the understanding they furnish in the important, fiendishly challenging setting of systems consisting of vast numbers of interacting elements, regimes in which quantum mechanics plays an essential role. Appropriately, numerous awards recognize Vedika's past accomplishments and future promise. I shall just mention the ones from the 2020s. Packard Foundation Fellowship, the Breakthrough New Horizons in Physics Prize, the Valley Prize from the American Physical Society, Macmillan Award from the University of Illinois at Urbana-Champaign, the Early Career Award from the U.S. Department of Energy, the Research Fellowship from the Sloan Foundation, all thoroughly deserved. Please join me in welcoming this evening's speaker, Vedika Khemani, who will tell us about quantum matter out of equilibrium, time crystals, and beyond.
Thank you. Thank you, Paul, for that extraordinarily kind introduction. And thanks to all of you for joining us on this beautiful evening. It's my great pleasure to be here today. I am a theoretical, slide. Okay. I'm a theoretical physicist, and I'm an organizer for the New Frontiers of Quantum Dynamics program that has been running here at the Institute for the past 2 weeks. This is a very exciting and topical area at the interface of several distinct subfields, ranging from condensed matter, quantum gravity, and quantum computing on the theoretical side, anchored by really breakthrough developments on the experimental front in fields such as quantum engineering and atomic, molecular, and optical physics. Today, I hope to share with you some really fun and exciting ideas that we've been focusing on in these areas. In particular, I'll focus my talk on new kinds of out of equilibrium phases of quantum matter. But before I get started, I really want to echo Paul and just say, even though my career is very young, I've been coming to Aspen for the past few years now. This is really such a special and unique place in bringing people together and allowing us to make connections across all of these different subfields, allowing us to debate and discuss ideas in this beautiful setting. So I specifically want to thank each of you for your support of the Institute, for your interest in our science, and for opening up your homes and your town to us every year, year after year. Okay. So let me start by giving you a backdrop of the physics I'll discuss today, which is driven by a simple yet powerful feedback loop between experimental breakthroughs in engineered quantum devices and fundamental theoretical developments in quantum dynamics. As you've no doubt heard from popular news articles and from various other public lectures here, we are currently at the dawn of a second quantum revolution. There's been tremendous progress in the development of engineered quantum devices across a variety of platforms, ranging from ultra-cold atoms to trapped ions, Rydberg atoms, and superconducting qubits. These represent the fruition of decades of tremendous effort across academia and industry, starting perhaps with ideas dating as far back as the 1980s and 90s on quantum simulation and quantum computing by the work of physicists such as Richard Feynman or Peter Shor and others. Now, much of these efforts are aimed at the controlled generation and manipulation of quantum entanglement as a resource or as a fuel to gain advantage in tasks ranging from computing to sensing to cryptography. One analogy that might be helpful is the dawn of the electrical age, was similarly driven by efforts to gain control over individual circuit elements, the controlled generation and use of electricity, which of course powers everything around us today. However, the control of quantum entanglement is much harder. It's much more challenging. And we're still very, very far from where we would need to be for tasks that you might read about in the news, such as factoring large integers or breaking quantum cryptography or internet cryptography. So, despite these challenges, what's really remarkable is that even in their current capacity, these platforms have already been revolutionary, not from the point of view of being excellent information processing devices, rather as new laboratory systems. In other words, as new physics experiments that have given us brand new capabilities to study and probe quantum matters, vast new regimes, specifically giving us controlled access to the dynamics, the out of equilibrium dynamics of quantum systems of many, many particles. And this is because the operation of any quantum device or quantum algorithm is fundamentally a non-equilibrium process. All of these devices, which are aimed at achieving this task, maybe several years in the future, are already developing groundbreaking capabilities to probe in a controlled way quantum dynamics. This, on the theory side, has focused our attention on deep and foundational questions in quantum mechanics, some of which, in fact, date back to the inception of quantum mechanics itself, which are now receiving renewed interest due to these extraordinary experimental developments. These range from developing a universal theory of quantum chaos, systems ranging from collections of interacting atoms, black holes themselves, to understanding settings in which systems may robustly fail to come to thermal equilibrium, which will play an important role in what we will discuss today, to discovering and formulating new non-equilibrium phases of matter, such as time crystals, which may defy all of our expectations from familiar laws of equilibrium thermodynamics, to uncovering new, perhaps physics-based insights for quantum algorithms. And of course, as always happens in science, the hope and the dream and the expectation very much is that these new theoretical insights will in turn generate fundamental new approaches for solving hard challenges, extraordinarily hard challenges in quantum engineering. So, in sum, the operation of a quantum device is fundamentally a non-equilibrium process. The experimental development of these platforms has fueled a focused interest in fundamental questions of quantum dynamics, which will, in turn, feed back into the development of new quantum technologies. So that was a lot, and I'll slowly try to unpack that in the rest of this talk, focusing in particular on theoretical developments in uncovering and understanding new types of non-equilibrium phases of matter. So before we step completely out of equilibrium, let's take a moment to really understand from the point of view of physics how we have traditionally thought of phases of matter in equilibrium. Okay, so at the broadest level, as scientists, we wish to understand and describe phenomena on all scales of space, time, and complexity, atomic nuclei to galaxy clusters and black holes and humans themselves. Now, a paradigm that we internalize very early on is that the workings of all matter are controlled by the same set of fundamental laws. So if we understood and uncovered those laws, then our understanding of everything else in nature would follow as a simple application. Okay, so in particular, if we understood those laws by studying elementary particle physics or math, then we could understand everything, including the human brain itself. Okay? So this is the so-called reductionist hypothesis. And fortunately, I would say fortunately, nature actually turns out to be much, much richer. Okay? This is not the approach that we take in condensed matter physics. The behavior of large and complex aggregates of many elementary entities can rarely be understood in terms of a simple extrapolation of the properties of individual constituents. Just like the behavior of a complex society cannot be predicted by studying a handful of individuals, the behavior of complex systems of particles, of individuals, of electrons can similarly cannot be derived by the knowledge of how individual particles behave. In other words, the whole is much richer than the sum of its parts. At each level of complexity, entirely new properties in physics emerge unpredictably and surprisingly from the level below. So, two familiar yet striking examples in nature are found in ant colonies and flocking birds. Right? Of course, an individual ant or an individual bird is not a very sophisticated being, yet large collections of ants or birds, all interacting with each other through very simple rules, can display rich collective phenomena. In condensed matter physics, we likewise study the collective emergent phenomena of large collections of many electrons or atoms, all interacting with each other through the laws of electrodynamics and quantum physics. Indeed, when viewed as a collective, the system composed of the same individual entities, in fact, organize itself into different phases. Right? So you could start with same kinds of atoms, the same kinds of molecules interacting with the same fundamental laws of physics. You could get a whole rich array of incredibly interesting phases of matter. So for instance, you could get the familiar phases such as solids, liquids, and gases, but you could also get new phenomena such as superconductors that could conduct electricity without any resistance. Okay? So take-home message is that a phase of matter is fundamentally a collective phenomena emerging from the interactions of many, many billions of interacting particles. It is simply impossible to speak about a single H2O molecule as ice, liquid, ice, water, or steam. Instead, collections of H2O molecules interacting with the same laws of physics and organize themselves into these different phases depending on the condition. Okay, so in other words, the ability to reduce everything down to simple fundamental laws does not then imply the ability to start from those laws and build up and reconstruct the rich universe that we see around us. And condensed matter physics aims to uncover the emergent richness of the phenomena and phases displayed by many particle systems. How do we actually do this? Okay, this is a very, very hard problem. You're talking about a system of billions of particles, all of which are interacting with each other. So you can't just study one particle and deduce something about the collective. So how do we do it, right? You might think, okay, why don't we just start keeping track of what these particles are doing? You'd very, very quickly be out of luck because of the exponential growth of what's known as Hilbert space, which is the state space that these particles can occupy. Think of a very simple model where each particle can be in one of two states. Okay, so this is denoted here as up or down, heads or tails, whatever, however you want to think about this. Now, one particle is in two states. If you have 8 particles, they can be in 2 to the 8 or 256 states. As soon as you get to a macroscopic number of particles, which is what you would study when thinking about quantum matter, 10 to the 23 particle, the number of states that these can be in is just hopelessly large. It's bigger than all known atoms in the number of atoms in the universe, right? So there's no way in which we can individually keep track of each of these different entities and try to describe the state of the system in that way. Instead, what we do, and all of the remarkable physics and understanding phases of matter, is built on the foundation of equilibrium statistical mechanics. Okay, and what equilibrium statistical mechanics does is allow us to say useful things about a macroscopic number of particles, 10 to the 23 particles, the air in this room, the number of water molecules in this bottle of water. And it does that not by tracking each individual microstate. So microstate is a detailed discussion, is a detailed description what each particle is doing. So for instance, if you wanted to describe what the position of the ith molecule was, or the momentum of the ith molecule, this is what I said, this just goes completely out of bounds very, very quickly. The other hand, many, many different microstates can still correspond to the same macro state, which is described in terms of a few coarse-grained properties of the collective. For instance, pressure, the volume, the density, the energy, things like that. So the approach that we take when describing physics in the framework of equilibrium statistical mechanics is to instead describe states that are characterized by a few macroscopic variables, okay? And the picture is that you can start with a given system in some state. So for instance, I could have started in this room with all the air molecules on one half of the room, okay? If there's a barrier and you created a vacuum on the other side by sucking all the air out. Now you lift the barrier, and there's many, 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 many more ways for the air molecules to spread across the entire room than for them to stay put on one side. Okay, so the number of different microstates that this system, the air in this room can be in, that is characterized by the entropy of the system, and this entropy tends to increase in time. Okay, that's the second law of thermodynamics. So systems tend towards equilibrium macrostates, which are governed by some competition between maximizing entropy and minimizing energy. Okay? So you could start with all your air molecules in this half. Over time, you wait, and then very quickly you find that the air in the room is a roughly uniform density. Okay, so if I had started by tagging some one particle in the room, I made it that Aspen green color, and then you saw what that one particle was doing, it would be zipping around like crazy. It would never settle down, okay? But the density, the overall coarse-grained pressure, the temperature, those variables do settle down quickly after being displaced. They reach a state of rest, okay? So there's a joke that my undergrad professor made, which is that a physicist counts as 1 to 10 to the 23. okay? Because you can solve the one-body problem, you can solve the two-body problem. Three-body problem is too hard for us. But when we get to 10 to the 23, we can apply the rules of statistical mechanics, and then we're in business again, okay? So this is the foundation of everything, that all of our understanding, okay? So when you're talking about solids, liquids, and gases, once again, you have these macro variables, which are pressure and temperature. Look at the equilibrium state defined by these macro variables, and then you organize these into phases of matter that you're all familiar with. In this phase of matter, so far I haven't invoked quantum mechanics at all, by the way, okay? So right now, if I'm thinking of the phase transition between liquid and gas, which anyone who's boiled a pot of water has encountered, you can see that just when the water is about to boil, it looks kind of maximally frothy, maximally fluctuating. Okay, so this phase transition from a liquid to a gas is a point which is driven by thermal fluctuations. Okay, you're trying to raise the temperature at that critical point. That transition is driven by thermal fluctuation. However, now I want to talk about quantum mechanics, okay, and need some other route, not just temperature, to try to drive these fluctuations and these competitions between different states that matter could organize themselves in, okay? And what's been extraordinarily interesting for the last several decades of thinking about quantum matter is thinking about phases and phase transitions driven by quantum fluctuation, okay? So one of the foundational principles in quantum mechanics is Heisenberg's uncertainty principle. And what Heisenberg's uncertainty principle tells you is that there are pairs of observables that are fundamentally incompatible with each other. You cannot, it's unknowable, you cannot simultaneously know what both those observables are doing. So position and momentum are two such observables. And the joke is when Heisenberg gets pulled over by a cop who asks him how fast he's going, I have no idea because I know where I am, right? You pulled me over. Position and momentum, position and velocity are fundamentally unknowable together. This is just one example of many, many different pairs of such incompatible observables. So if your system, the energy of your system, is described by terms which are fundamentally incompatible, for instance, if you're trying to lower the energy to get to the lowest energy state in your system, where quantum effects are most pronounced, you cannot simultaneously make all of these terms happy. In fact, you cannot even simultaneously know what all these terms are doing. So that competition, this is one such parameter that can drive, this is a model, it's very, actually a very simple looking model that displays very rich physics. This is a model for superconductivity, and temperature is one axis, and you can drive a phase transition from a phase of a magnet, an antiferromagnet in this case, to a different phase by raising the temperature. And if you did that, you would see kind of similar thermal fluctuations. This would be driven by thermal fluctuations, just like the phase transition between water and steam. But you could actually be at zero temperatures, as cold as you can be. You're just trying to minimize the energy of the system. And then because you have these fundamentally incompatible quantum observables, your phases of matter can organize in various interesting ways, and you can get this quantum phase transition, which is driven by quantum fluctuation. Okay, so trying to understand phases is diagrams such as this, where quantum mechanics plays an important role, has been an enormously productive exercise in condensed matter physics. And we've uncovered all sorts of interesting phases of matter. There's, of course, semiconductors, which has fueled our modern age of classical computing. There's superconductors. We may not have high temperature superconductors yet. I know there was a lot of buzz about this in the media recently. But even having the low temperature superconductors that we do have been very, very useful for everything from MRI machines to maglev trains. Then the last few decades have been driven by very exotic kinds of equilibrium phases of matter. These display a kind of topological order. Okay, so this is, in a few slides, I'll tell you about order that's defined through broken symmetries, which is how we usually think about order. This is a completely new type of order, and this is underpinning the physics of these phases underpinning a lot of the types of systems that these quantum devices are trying to build. Okay, we're not there yet, but this does form a basis for a lot of the effort. Okay, so as I said, this has been an extraordinarily productive, rich enterprise. There's still a lot to be discovered in even just thinking about equilibrium phases of many interacting quantum particles. But if you think about the full quantum mechanical description of systems of many particles, equilibrium phases, despite their rich variety, occupy this tiny, tiny, tiny corner of what's allowed by the laws of quantum mechanics. Everything around us is out of equilibrium. If you open a quantum mechanics textbook, there are two basic operations that this quantum mechanics textbook will teach you about. The first is unitary time evolution. Okay, so this is, you have a quantum system. What are the rules that tell you how the system changes in time? Okay, that's one fundamental aspect of what we want to think about. And the second is measurements, which are denoted by this little dial here. Okay, and measurements in quantum mechanics, we'll come to that later if we have time. They have they have this crazy effect, which is completely different from how our classical systems respond to measurements. Okay, this is what prompted Einstein to say quantum mechanics can't be right because it's spooky action at a distance. When you measure a quantum system, you fundamentally change it. Okay, so the most general quantum mechanical evolution that you could think about is unitary time evolution interspersed with measurements. Okay, and there's this enormous space for understanding what are the collective emergent phenomena that we can be asking about in the dynamics of these many interacting quantum particles that are evolving in time. So, this is an extraordinarily large space, but we also have very, very few tools to answer these types of questions. As I said, Hilbert space grows exponentially. So the reason that we've been hanging out here, because there was good reasons to do that. This is where our experiments were. This is where our theory was. Okay, this is where we're grounded. As soon as you step out here, it becomes very, very hard to say anything at all. Okay, and what these new types of experiments that I mentioned are doing for us is giving us access, experimental access to this vast new space and allowing us to explore it. Okay, so in some sense, there's a paradigm shift in moving away from what is nature giving us? Here's a material. What did the equilibrium quantum mechanical properties of this material teach us? To move away from that, to ask what's allowed by the laws of quantum mechanics. Okay, how do we build systems that could allow us to probe what's allowed by quantum mechanics, even if it doesn't exist in some natural state in nature in equilibrium? Okay, so for the next section of my talk, I'm going to talk about one paradigmatic example of an out of equilibrium phase of matter, which is a time crystal. Okay. So. Okay. So this clearly, in full disclosure, I didn't come up with the name time crystal, but this clearly captured the public imagination. There's a lot of, if you talk to someone, one of the first questions they'll ask is, "Oh, can this help us with time travel?" And no, it can't. I'll very soon get to a more physics-based definition of what a time crystal is. We actually gave it a fairly boring name. We called it a pi spin glass. Okay, but let's stick with time crystals for this public lecture. So before I give you the more kind of physics-based definition, what should you have in mind when you think of a time crystal? This is a system whose state repeats periodically in time. And if you're being really proper about it, then really you would want it to repeat periodically in time forever without any net input of energy. Okay, so imagine that you had this pendulum clock and imagine that you wound this up and then it could run forever without you needing to ever wind it up again. So This, of course, sounds perilously close to a perpetual motion machine, which people have been trying to build for many, many years, well before the laws of thermodynamics were even discovered. And if this sounds too fantastical to be true, it is. And perpetual motion has indeed been roundly rejected by the laws of thermodynamics. Okay, so the setting in which we're going to see this kind of behavior is going to be a very different setting. Quantum mechanics will play a very significant role. And it's going to be in a setting in which systems simply do not reach thermal equilibrium. Okay, so I don't want to say that laws of thermodynamics are broken. In fact, we're working in a setting where the laws of thermodynamics would simply not apply. Okay, but before going into all of that, let's talk about this name, time crystal, and specifically, what is a crystal before we talk about what a time crystal is. So, as lay people, you think of crystals, you think of these pretty objects which are there in all the shops around Aspen. But when a physicist thinks about a crystal, you think of something different, which to me at least is even more beautiful. Okay, so for a physicist, a crystal is a phase of matter that is defined in terms of fundamental symmetries of nature. So before I go there, let me tell you about this extraordinary work which really underpins our understanding of almost all phases of matter except this kind of topological class. And this was work from Khemani Noether, and she drew this very, very strong and powerful connection between symmetries in nature and conservation laws. Okay, so what she proved is that all conservation laws come from fundamental symmetries in nature. Okay, so energy conservation is something you learn about in grade school. Okay, the energy of a system cannot, if you have some system that's not being pushed on or pressed on in any way, or you're not extracting any energy from it, that then the energy of that system is going to be conserved. But this principle of energy conservation actually comes from a fundamental symmetry of nature, which is that of time translation symmetry. Okay, so when Newton was coming up with Newton's laws, okay, that was in the 1700s, Newton's laws are still applicable today. Okay, the laws of nature are the same at all times. And this time translation symmetry is what's responsible for energy conservation. Okay, likewise, momentum conservation is something we're all familiar with. If you don't press the brakes on your car, you're in a perfectly frictionless road, your car will just keep going forever at the speed at which you started it. Okay? Momentum conservation comes from symmetry of nature, which is spatial translation symmetry, which is that the laws of nature are the same everywhere. Okay, if you do an experiment here in Aspen, or if you do an experiment at Stanford, you don't expect the fundamental laws of nature to change. Okay, some constants might change. The gravitational constant might be different slightly, but the actual F equals ma law is not going to be different in Stanford or in Aspen. Okay, so all other conservation laws that we're familiar with, charge, angular momentum, are similarly associated with symmetry. So in physics, when we talk about distinguishing between different phases of matter, what we're really talking about is whether those phases respect or break those intrinsic symmetries of nature. So a crystalline solid is one that spontaneously breaks its translation symmetry and by forming this periodic arrangement of atoms, whereas liquids and gases are statistically symmetric, and hence these are two different phases. Okay, this is often a little counterintuitive because when you see a crystal, you're like, wait, isn't this very symmetric? Why am I saying that this is breaking the symmetry? Okay, and the reason is that it's breaking the symmetry because it's arranged itself in this pattern where you have an atom and then you have some space, and then you have an atom and then you have some space. So it's not every location in physical space does not look identical. So look at the seats that you're sitting in. Okay, this is like a kind of lattice. Okay, it might look that this is a very regular arrangement of seats, but there's a place for you to sit on there, and there's no place for you to sit on between those two seats. Okay, so this is a crystalline arrangement which has broken the continuous translation symmetry of space. Laws of nature would not be different whether an experiment was conducted there or like a micron away from there. Okay, but the arrangement of the seats has broken that down. That's why a crystal spontaneously breaks translation symmetry, whereas liquids and gases, statistically, if you take a snapshot, they look like they're in certain positions, but statistically, they have no spatial variations. They're continuously distributed through all of space. Liquids and gases are in a different phase. Okay, and spontaneous symmetry breaking really is an exemplary example of the phenomena of emergence that I was telling you about before, because the laws of nature tell you that there is translation symmetry. Okay, so the fact that a system of many interacting particles, through those interactions, arranges itself in a configuration where that fundamental symmetry of nature is spontaneously broken is an example of emergence, and it's in fact the example of emergence. Okay. So what do we want a time crystal to do? Just like a spatial crystal breaks the spatial translation symmetry of space, shows you this periodic arrangement, what you would want a time crystal to do is to break the time translation symmetry that's inherent in the laws of physics and show you changes or temporal variations in time. Okay. Because this is a crystal, we want this temporal variation to be periodic in some way. Okay, so your system could start off in some state, and it could go to a different state, then it could come back to this state, but you want some periodic repetition in time of the system, and you want this to happen spontaneously. Okay, it's spontaneously breaking intrinsic symmetries that exist in nature. So, why was this thought to be impossible, right? This was thought to be impossible, again, because of the laws of thermodynamics. To understand that, let's just go back to the example of the grandfather clock and the pendulum. Okay, so I said that the cartoon picture of a time crystal is a pendulum clock that never needs to be wound up again. So why would that not be possible? First, there's always dissipation, there's friction. Okay, so your system is going to dissipate energy. You're going to need to pump more energy in it. You're going to need to buy batteries for your battery-operated clock that you can buy from Amazon. That's the first law of thermodynamics. Okay, the perpetual motion will need a source of energy. Let me play theoretical physicist for a moment, and let me say that I've put my pendulum in a perfectly frictionless bell jar. It's a vacuum. There's no friction in any of the ball bearings. I've stepped and I've kind of stepped away from this requirement of needing this energy input because of dissipation. Even if I do that, the second law of thermodynamics gets in the way. Okay, why is that? Because again, think of this pendulum bob. This was described by just one mode, okay, the center of mass mode, the center of this pendulum. And indeed, that one mode would keep swinging forever if we were in this frictionless vacuum jar situation. And that would be fine. We have the examples of a single particle showing you time dependence all the time, all over in quantum mechanics. You can take one particle with a property known as spin, stick it in a magnetic field, and it's going to rotate forever. There's nothing special about that. What's special is that when you bring in many, many, many interacting particles, okay, again, here we talk about interactions, many particles, then entropy, okay, your system is going to want to go to an equilibrium state which maximizes entropy. And there are just many, 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 many more ways for the system to distribute its initial energy, which might be in the center of mass mode, across all the different internal modes in the pendulum, okay? You can think of this pendulum as composed of many atoms inside it, each of which are interacting with each other. So that's depicted through these different balls and springs. Over time, the energy that you put in that center of mass swinging mode, it's redistributed into all of these other internal modes of the pendulum, and it eventually is going to come to rest. Okay, this is the statement of the system coming to rest in an equilibrium state. Things tend towards equilibrium states. And those are by definition not moving in time. The macro states are not moving in time. So if I want a many-body system that's going to continuously, constantly show me some time dependence, I fundamentally need a way to evade the second law of quantum mechanics, of thermodynamics, okay? And we're going to rely on quantum mechanics in order to do this. So let's step back and look at quantum particles. Okay, so our classical intuition of a particle is that a particle has a position. That cup of water is right there. But quantum particles, okay, really, really tiny quantum particles, these are actually better thought of. There's a wave-particle duality, and this particle is really a probability wave, okay? What this wave is telling you is the probability to measure that particle somewhere in space. And until you measure it, that particle is in a superposition of being in all of these different positions. It's neither here, nor there, but it's everywhere and nowhere at the same time until you make a measurement and you look. Okay, so this is the famous example of Schrodinger's cat. Schrodinger took his cat and was very mean and locked the cat up in a box with a vial of poison. And the point is, until you open the box and look, you have no idea whether or not cat consumed the poison and died or didn't. Okay, so the cat is in a superposition being dead and alive until you look. Likewise, quantum particles have this probability wave that's spread in space, and they have this probability of being here and there and here and there until you look. Okay. Why is this important? Because when you think of waves, you think of interference patterns. Think of constructive interference. You think of destructive interference. Think about the last time you threw a pebble into a pond of water. Okay, you saw ripples. Those ripples are patterns of constructive and destructive interference. So by likewise arranging patterns of constructive and destructive interference for these probability waves that represent my particle, you can create situations in which a particle which would be everywhere, as spreading out by the laws of thermodynamics would dictate, that's simply not allowed. Okay, it could get localized. It could get localized to one location. Let's see how that works. Okay, so this was the Nobel Prize winning work of Phil Anderson. And right now, he's just thinking about one single particle. I'm not talking about many particles yet. Okay, I'm talking about one single particle represented as this probability wave. Okay, suppose I gave my particle an energy which was there, and this is some potential energy landscape. Okay, it has hills and valleys. So if you're down here, that's a very low energy configuration. If you're up there, that's at a peak. Okay, so if you're a classical particle, okay, if you're just thinking about from our classical intuitions, you start off at a low energy, and your total energy is the sum of your potential and kinetic energies. The total energy in classical physics never exceed the potential energy. So if you start off in some trough somewhere, you remain stuck in that trough. Okay. On the other hand, if you start off with an energy that's above all of these different peaks and valleys, then you're totally free. You're delocalized. You can be anywhere you want. Okay. Maybe you'll slow down a little as you're going over a hump. You can be everywhere. Quantum mechanically, the remarkable thing that Phil Anderson showed is that you can have the gentlest of ripples. Okay. So this is some disordered potential energy landscape. You can have the gentlest of ripples. With this gentle rippling, no matter how weak this rippling is, a quantum particle can get stuck, okay? It's not going to explore all the space available to it. And the reason it gets stuck is because of a pattern of destructive interference. You can think of this as a wave trying to move forward in space, and every time it encounters one of these barriers, a little bit of the wave is reflected back. And when you add everything up, you can arrange for a situation, and in fact, in one dimension, no matter how gentle your ripples are, your particle always gets stuck in that corner. Okay, this is just remarkable. This is what Phil got his Nobel Prize for in this is work done in 1958. When he came up with this, it was really met with a lot of skepticism, but it's true. Okay, and this is the facet of quantum particles that we're going to use arrange for a situation in which systems are fundamentally out of equilibrium. Okay, so as I said, this is a situation where I'm talking about just one particle. This was already figured out in 1958. The years since 1958 to 2023, there has been a lot of robust debate on whether or not this phenomena, where systems get stuck and survive when you're talking about not just one particle, but many, many, many interacting particles. Okay. In that situation, getting stuck would mean that you're starting with a system of many interacting particles. You can start it off in some configuration. Again, for instance, all the particles could be in the left half of the room. Then you wait, they don't spread out and take over the entire room. Okay, it just remains stuck. So this has been a very, very active topic. This is the subject of many body localization. It is by no means settled. However, what we do know and what we have seen experimentally, I'll show you that in the next slide, is that there are many, many situations in which, even if not forever, for very, 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 very long times, longer than possibly the age of the universe, certainly longer than any experimentally accessible timescale, you can see this phenomena of many interacting particles getting stuck. Okay? There are certain settings in which we believe that this could continue forever. At that point, this is mostly a theoretical debate anyway. So let me show you actual data. This is from a paper from 2016 in Emanuel Bloch's group. This is an actual experimental image of quantum particles in an atomic trap. Okay, so each of these dots represents a quantum particle. And what the experimentalists did is they set up the system with all the particles, again, on the left half of the trap, just like you would do if you were thinking about air molecules. And then they let the trap go, they waited, and they saw what happened. Okay, and this is a system of interacting quantum particles. At this value of the parameters, when you have many, many strongly interacting particles, you actually need to make the disorder, which is the relative strength of these hills and valleys, quite strong in order to see this effect. It's not like one single particle where your disorder can be arbitrarily strong or weak and you still see it. But in this situation, they had weak disorder. So these particles behave like you would expect from your general intuitions. Okay, you started your system off, it spreads out from the left, moves towards the right, and you wait a while and you see that the density is roughly uniform everywhere in this trap that they had. Now they cranked up the disorder. They again started with the same configuration, and they waited as long as they could in their experiment. And again, this is real data. It has experimental imperfections. And you see that the particles have not spread out. Okay, they are preferentially still in the left half of the trap. And you can see this was the experiment run for the same time with the same initial conditions. And what I was changing, what the experimentalists were changing, was how strong this disorder was. Okay, here is a system of many interacting particles where thermalization, the approach to this equilibrium thermal state, can be dramatically slowed down by the addition of disorder. This experiment has a finite lifetime. This data cannot tell you whether, if you waited infinitely long, whether these particles would or wouldn't spread out over the entire trap. The theoretical arguments that we have when what time scales we expect that to happen on. And again, this is still a very active area of research. The fact that you see this dramatic effect in a real experiment is unmistakable. Okay, and this is what we used in order to create this time crystal. Okay, so under the right conditions, now you need to get into a lot more technical details, which I won't do, where you not only have the phenomena of many body localization, you're also starting to drive the system in time. The system can remain localized, and it can oscillate between different localized states without ever absorbing any energy from the drive. Okay. And if your drive had a particular period, which was T, what you see is that you can change all sorts of parameters. You're not fine-tuning the system in any way, but even after you change all of those parameters, the system responds at a period which is 2T. Okay, so this is my configuration of particles. They're all localized or stuck in the state in which they started. Then you wait one period of your drive, they flip to a different state. Then you wait another period and they come back. Okay. So it's like if you already started in this lattice, which is this auditorium seats, and if you spontaneously arranged yourself in a pattern where every other seat was occupied. Okay, so now you had a smaller symmetry to begin with, which was in going from one seat to the next, and your system spontaneously arranged to break that even further. Okay, but the fact that it shows this kind of robust oscillation in time, it can change parameters. There's many, many interacting particles. The fact that this happens fundamentally relying on the inability of this system to reach thermal equilibrium, okay, or localization. So how to exactly formulate, how do we like theoretically formulate what this means, what this new, how do we even define how to look at this phase, how to characterize it? All of this was work that we had to do, but we did it kind of very much motivated by these fascinating new experimental capabilities. Yeah. And as I said, this is a time-dependent quantum system. It's a very delicate quantum system. It's not observed naturally in any material in the wild, which is in equilibrium, but quantum simulators, quantum computers, which are still very, very nascent and not useful for any quantum computation, are nevertheless very useful for seeing this kind of phenomenon. Okay, so quantum simulation is the most promising near-term application of a quantum computer. And quantum computers have this kind of gate set. We could engineer a particular type of interaction, a particular type of drive, look at the system in time, and we were able to exploit. This is a very simple signature I'm showing you, where in one value of the parameters, your system just quickly settles down and doesn't show any time dependence, whereas in a different value of parameters, which does correspond to the many-body localized time crystal, you can see these oscillations, which again last as long as the lifetime of your experiment. Okay. So that was one thing. I won't tell you anything about this, but we've gone much beyond just many-body localization. We're starting to think of this full space of unitary dynamics and measurements. We're asking about what are different kinds of non-equilibrium phases you can arrange. And in this case, again, to evade the second law of thermodynamics, to evade this inexorable growth of entropy, we need some other mechanism now. And here it's measurements that are playing that role. And in a paper that we just posted a few months ago, we're exploring various different phases now defined by different quantum information theoretic properties, such as the ability of the dynamics to generate entanglement or to serve as a resource for teleportation. And we're looking at this whole new playground of physics on these platforms and in theory. Okay, I'll skip over my slides on why a quantum computation is fundamentally a dynamical process and why we need to really exploit a very, very specific type of dynamics in order to get a useful answer in a quantum algorithm. But I'll leave you with the summary of my talk, which is that we're in this extraordinarily interesting time where these new types of quantum experiments, these new devices, are simultaneously being developed for their promise as information processing devices. They're also brand new classes of physics experiments. And this has just opened up a vast new arena with much to be learned and discovered. And in doing so, we're also uncovering a very deep convergence in ideas and language across fields such as quantum information, quantum gravity, and condensed matter, which places like the Aspen Center really help us. Thank you.
Yeah, captivating talk. We have a little bit of time for questions, but what I'd like to do is have those questions But anybody who needs to leave to catch the crosstown bus or anything like that, please feel absolutely comfortable to do so. You on with questions in case there are any after that. So please, fire away with questions. Yes, over here.
What are the? I know that like it's just fun concepts, I guess. What theoretically are the ideas? Like, is it in terms of what time? Like, is it weather patterns? Is it stuff? Like, what can this be applicable to?
Okay, so the question was, what can this be applicable to? So as you said yourself, you know, the thing that I find most interesting about it is the theoretical beauty of this. That, you know, there's this new phenomena that we thought was impossible. Quantum mechanics gave us a way to find it. I think in the near term, probably what it's most likely to be applicable for is different types of approaches or designs for quantum engineering. Okay, so going back to this kind of feedback loop that I was talking about, this happens to be a phase which is very, very robust, very, very stable. Okay, and be many, many years before or ever, if you figure out whether that can actually be exploited in some useful engineering task. When you do have a phase that's that robust, we generally find some applications. I also say, you know, the types of drives that we used that showed this phase, they have particular sequences that actually already are used in things like that. There are these various echo sequences that are used in engineering all the time anyway. Okay, so I would say the most promising near-term application for this type of physics is in new insights, either for building qubits for quantum engineering or even for types of dynamics that may give you a useful computation. Okay, so this is coming back to this slide here where people talk about quantum computing. You know, the popular media is like, well, quantum mechanics, you have superposition. Your particles can be in every possible state at once. You run your algorithm and you can get every possible answer at once. Okay, but this is not right, because you have to measure something. And when you measure it, you just sample and get one answer. You don't get all the answers. There are very, very few useful quantum algorithms that we know of. And in order to get that, you need to choreograph a very special kind of entanglement dynamics in order to get your system to actually constructively interfere on the right answer. Okay. The general principles for when we can do this still, in my opinion, very, very, you know, it's a completely open arena, because we only know a handful of problems for which this can be done. So understanding different settings for quantum dynamics, when dynamics can show you interesting behaviors, might down the line, even if it's not exactly time crystals, help us in thinking about new classes of quantum algorithms as well.
Two questions. One's specific. You spoke about disorder, and that one experiment that galvanized a lot of your current research with the atom traffic. You referred to that as how the potential varied. I want to know what the disorder was in particular for that experiment.
Yeah.
Then the second thing on this video, I saw a talk by Sebastian on quantum alchemy. A lot of overlap. I just wondered if she's more closely with her, you know.
Okay, so the question was, going back to this experiment that I showed on the quantum traps, what exactly was the disorder? This was a system of interacting atoms, and the interactions, you know, so they had some hopping terms. So it's like, you know, if you have an atom in one location, it can hop to neighboring sites. It had some interactions. Then it had a potential well that the atoms were sitting in. The beauty of these experiments is that they can actually go in and atom by atom control what that potential energy landscape looks like. So, you know, showing you this picture of hills and valleys for one dimension, it actually doesn't look so different. And the experimental breakthrough there was being able to, on demand, come up with this pattern of hills and valleys. And the strength of the disorder would be the relative depth of these hills and valleys. And that's what you're tuning. Oh, the expert in doing this is in the audience. It's something called the DMD. It's an optical device, and I don't know details of engineering. Yeah.
It was a laser beam with random spatial pattern.
Yeah, exactly.
The disordered environment for the atom. The laser beam is a random spatial pattern. Okay.
The answer is it's a laser beam with a random spatial pattern, yeah, which is giving you this landscape. Yeah, and then you asked about overlap of this work and Suchitra Sebastian's talk from a few weeks ago. I haven't seen that talk, but my understanding is that she also thinks about quantum materials, but more in the setting of equilibrium. There's, again, lots of interesting questions to be understood there, but these are actual quantum materials rather than these engineered quantum devices out of equilibrium.
Other questions? I have one.
Yeah.
You explained beautifully the idea of crystals and the fact that the translational symmetry is spontaneously broken. Is time translational symmetry spontaneously broken here, or is it broken by the drive?
Okay. It is spontaneously broken. Yes. The question is time translation symmetry spontaneously broken in a time crystal, or is it broken by the drive? And it is spontaneously broken because indeed the drive is giving you a periodicity. So the drive is explicitly breaking that symmetry. That's like creating a lattice to begin with. Then the time crystal is further breaking that discrete symmetry. So now you don't have a continuous symmetry. The drive tells you that the equations of motion only look the same after every period. But the system is responding at twice that period. So like if you set up this lattice and you occupied every other seat, setting up the lattice would have broken the symmetry explicitly. Then if you only occupy every other seat, you're spontaneously breaking that discrete symmetry down further.
Other questions or comments? Yeah, John.
Do all non-equilibrium quantum systematic break some form of spatial or temporal symmetry, or are time crystals unique in that?
Okay, great question. The question is, do all forms of non-equilibrium matter break some form of spatial or translation symmetry, or are time crystals unique in that? So they do break. Okay, so no, not all forms do that. So for instance, in this setup, this is still a driven system. It's still out of equilibrium in the sense that there's a drive there. It very quickly settles down into an equilibrium state. Okay, so just by driving something out of equilibrium, you're not guaranteed that it's going to show you this kind of spontaneous oscillation. The other answer is that it depends on how you break, what kind of symmetries your system had in the first place. So for this particular problem, one way in which we were able to create this is by putting in a disordered landscape. If you have a disordered landscape, then your system doesn't have spatial translation symmetry to begin with. So there's nothing there to break. Okay. So disorder is one kind of way we know to create this kind of physics. There are different approaches we can take by making measurements and so on. In all of those settings as well, what the underlying symmetries of your problem are can be quite different to begin with. And you can get both phases that either there's no symmetry to talk about, or you can get phases that respect those or break those.